Now that we've got a good understanding of electric potential and electric field strength and how they're related, we're going to have a look at a graphical representation of this scenario. So you can see there I've got a diagram of parallel plates. Just draw your attention to the fact that the plates are in the opposite orientation to what I've been drawing them previously. So positive plate is on the right, negative plate is on the left. That's because we're going to graph electric potential versus distance with respect to the negative plate or the zero potential plate. Electric potential versus distance. And it just makes it a little bit easier to see here if the distance from the negative plate is measured from the left across to the right, just a little bit easier to link those two ideas. So when we graph that relationship, because it's a uniform field, what we will see here is a directly proportional relationship. So if we have the potential on the vertical axis, so that's the value V, and it's measured in the units of volts, and across the horizontal axis we've got distance from the 0 volt plate. And that's the quantity D, and that's measured in meters. In this case what we would see is that as we move from the left to the right, we'd have all these equipotential surfaces here. So we'd have one down the middle that would be half of the potential difference between the plates, have another one there, so on and so forth. So as we move across to the right, as the distance increases, the potential also increases, and so we would have a directly proportional relationship there. Now the gradient of that is a useful quantity to identify. So the gradient of this graph and if you think about gradient, it's the change in the vertical axis over the change in the horizontal axis, so delta V over delta D. Notice here that, just as a side note, if we look at the fact that it's linear, this will actually give V on D, which is equal to the electric field strength between the plates. So in that sense, if you imagine that we sort of had this, the value at the top here is the potential between the plates, and the value down here is the distance between the plates, then V on D would be equal to E. So just a little side note to keep in mind there. Want to take this a bit further than that though. The other thing here is that the electric field strength here is in the opposite direction to the increasing potential. As that value of D increases. So what that means is that if we're going to look at the electric field strength as a vector, we then have a relationship here that the electric field strength is going to be the gradient of that graph, so delta V on delta D, but the direction is in the opposite to the to that increase of the change in potential. So we have that as a relationship. You'll notice I'm highlighting it. It's one of the ones that's in the data booklet. So the electric field strength is the rate of change of potential with distance, but in the opposite direction. If we then graph that value, so if we graph the electric field strength versus the distance, we'd have a graph that looks like this. And so on the vertical axis we'll have electric field strength, quantity is E, and it's measured in this case in volts per meter. Remember that the other units that we could use for electric field strength are newtons per coulomb, and it's still going to have the distance from the 0 volt reference point on the horizontal axis, and that's still going to be D, still measured in meters. And you'll notice here that because we've got this negative gradient value, what we would see for the electric field strength is that it would be a line down here somewhere, where that would be the size of the electric field strength would be E, and so the negative there indicating that it's a vector in the opposite direction. One other useful quantity here too, if we consider then if we take that relationship that we've got there and we just manipulate it a little bit, if we take the vector E and multiply it by the change in distance, we actually end up with the value of negative delta V, so whatever the change in potential is. Now if you take these two quantities, E and delta D, and you look at what we've got on the graph here, that means that we can look then at the area under a curve. So the area under the E versus D graph gives the quantity of potential difference. So just to tie this off, if we have, say, a distance that we're looking at here, let's say that's the distance between the plates, we might then look at the fact that we'd have, we could go down here. If we then calculate the area, so all of this area under here now represents that value of negative delta V. Because it's below the axis, it'll be a negative area, so effectively the two negatives cancel, and so the value of the area there tells us the size of the potential difference between the plates. In the next video we'll take this a little bit further and look at a field that's non-uniform.